Welcome to today's AI seminar. We have Professor Linglong who will discuss conformalized fairness via quantile regression. So Dr. Linglong is a professor in the Department of Mathematical and Statistical Sciences at the University of Alberta. He holds a Canada Research Chair in Statistical Learning, a Canada CFAR AI Chair, and is Fellow of AMI. He is interested in the analysis of high-dimensional and neural imaging data, statistical machine learning, robust statistics, and quantile regression, as well as artificial intelligence for smart health. Now, welcome, Dr. Linglong.
Thank you, Tim Payne, for the introduction. And I guess I'm the last speaker for this semester. And also, I'm speaking at a very delicate time. I think most of AMI fellows is enjoying their AMI lunch right now. And also, I'm giving this speech after Brazil just been beat up by Caradel. And yeah, I hope you would be able to enjoy my talk and to So today I'm going to talk about this conformalized fairness via quantile regression. So this is a joint work with my PhD student Mei-Chen, Lei, my former PhD student Deng Deng, my colleague Bei, and also my collaborator Wu Long. And this research was under the theme of Canada-UK Artificial Intelligence Initiative. And we have this project called BIAS, Responsible AI for Gender and Ethnic Labor Market Equality. So the work was supported by these two universities, University of Alberta and the University of Essex, because this grant is an international grant. And in Canada, mainly it's by SHERC. At UK, it's Economics and Social Research Council. And of course, AMI and also NSERC. Now, I will first give some introduction about the existing literature on these findings. And then I will look at our methodology, which is the sort of quantile fair prediction. And not only that, afterward, I will give you our proposed method, how to do this prediction interval, in a sense, how to quantify our fair quantile estimation. Now, why fairness? This algorithmic fairness has received increasing attention, especially nowadays, and in a lot of socially sensitive domain and high-stake fields. For example, for the job, employment, for criminal justification, for loan approval, for credit score, and so on. And this sort of fairness is part of we call it this ethic of AI, or some people call it trustworthy AI. Now, for example, let's look at a situation. We have a loan credit model, and we want to build a credit model purely based on income. And so we have these two kinds of group. We have group people pay the loan, they pay their full loan in time, and otherwise it's defaulted. Those who are not able to pay back their loan and defaulted. So our aim is to set up a sort of threshold, income threshold in our training set to decide who should get the loan in the future. Of course, what we can do is we can pull them together and we set up a common goal, a common threshold, and then below the threshold, we call it negative. Then those people don't get the loan. Above they do get the loan. But is this going to be a fair decision? Is this fair to all these, let's say, all this group of people? Maybe not. Maybe yes. But let's first look at what kind of fairness we are talking about. Here we're talking about this demographic parity fairness. So for this kind of fairness, what's our goal? What do we want? We want our prediction to be independent of sensitive attributes. And here the sort of sensitive attribute is whether they paid their loan or not, whether they get default or not, And the key point is if they get defaulted previous, maybe they probably should get, should get less credit, but they shouldn't be punished forever or heavily punished. And therefore, maybe we should set up different sort of threshold for these two group of people, to be fair to these two groups. Now, here we look at this demographic parity fairness. Of course, fairness is even in social study, it's kind of challenging to define fairness, and it's important to have appropriate measure of this sort of fairness. And we can have different fairness. For example, we could have individual fairness. Okay, individual fairness. What does that mean? That means those individuals, if they are similar, they should be treated equally. Another fairness is sort of causality-based fairness. Causality-based fairness. This requires some domain knowledge to develop a sort of fair causal structure. And to build this causal structure, we need this domain knowledge. A third one is sort of group fairness. And we are looking at sort of equality for groups as a whole. And for this kind of fairness, we can have this demographic parity, and which we have talked about already. And we can also have this equalized odds. Okay, usually this is used in classification. We can also have this sort of group risk equality, and this is the group fairness. Of course, there are many definitions of fairness. For example, recently in federated learning, and they have this sort of proportional fairness, yeah. Now, how do we achieve fairness in our algorithm? To build this sort of, for example, here we look at this regression or classification. To build a fair regression or classification, there are kind of three kind of approach. The first approach is sort of a pre-processing approach. The key here is we transform the data to remove the unwanted bias. So that's why it's called pre-process, before we apply any algorithm. Okay, and we transform data and we remove the unwanted bias from the data, and then we can, because the data has no bias, and we apply the regular algorithm, and then we can get the fair result. We can get the fair result. result. The key step is this discrimination-aware pre-process. And in this step, we remove those bias. And this is the first kind of approach. The second approach is in processing approach. For this kind of approach, we incorporating this fairness constraint into the training step. Okay, and so when we process or when we train the model, and we sort of this bias aware, fairness aware, and we put this fairness constraint into our training. Therefore, we can get this fair result. That's the second approach. And then the third approach is post-processing approach. Okay, post-processing approach, and we just leave the data alone, leave the algorithm alone. We train our model, and we get predictor, and then we modify our predictor or modify our classifier so that we can achieve the fairness. So we can see the fairness. So that's the key step is this discrimination, reducing post-processing. In this literature, in this project, we actually use this sort of post-processing approach. And here, for example, we look at a sort of regression situation, and this is a paper, I think, published in 2020 or 2021 names. They have this sort of pipeline for fair mean regression, and the key technique here is this sort of Wasserstein to very center technique. So what do they do? And here, let's suppose we have two groups, okay? And we have two groups. So the sensitive variable S have two groups, 1 and 2, okay? 1 and 2. And this is the post-processing. So we first train our model, okay? We train our model on covariance X and also sensitive variable S. Then we get our regression model F. We get our regression model F. Then we look at the distribution of our predictor F hat on sensitive variable S equals 1 and also sensitive variable S equals 2. We look at these two distributions. We have these two sensitive variables, and we can sort of estimate the cumulative distribution function. Of course, there are many methods to estimate, and for simplicity, for simplifying, we can just use a empirical distribution. Okay, and we also estimate the quantile function of this F hat, and we estimate the distribution function, estimate the quantile function, and then through this sort of very center technique, we can combine this two group CDF and QF so that we can get a fair estimate, for these two groups. As you can see here, the post-processing reflect on after all the regular training, learning, then we do something with respect to the sensitive variable so that we would be able to get a fair estimate. That's why it's called, post-processing. And personally, I actually like this post-processing very much because, we don't interact with this training, and it can be easily to apply to any, any statistical learning method. Now, this paper is well received, but you may notice at the beginning, for me, I'm a statistician, and one of my research area is sort of robust statistics and quantile regression. And when this method is based on mean regression, but you have to think about, why mean, and also in practice, actually, a lot of people don't like mean, right? You think about your income, and if you just look at the mean income, you will find if you are quite poor, then you'll be mean out, right? And it won't be able to reflect that you are on the tail. On the other hand, this quantile actually is more informative for heavy tails, and it's very informative, very applicable, especially data are heteroscedastic or lake of Gaussian, and also for some situation, the mean does not even exist. Mean is undefined. So therefore, sort of a mean regression won't apply. It's not applicable at all. It's not applicable at all. So then there are many other reasons. We want to use quantile instead of mean. Like I said, quantile exists for any distribution, right? And also, quantiles can be defined for any totally ordered space, and the quantile can also be done sequentially, and we can get p-value for testing difference in quantile, and so on. And many reasons, for the repeating of quantile instead of just look at the mean, Now, and also in particular for this sort of fairness, like I said, in many situations, the unfairness may not exist in the mean. It may exist at different parts of the distribution, or let's put it in this way, it may exist at different quantile levels, and maybe in the left tail, but the very, like for example, for the income very, very low. For those parts, that's the fairness we need to look at more heavily. And so let's give us a lot of reasons why we should look at the fairness of quantile. So in particular, what kind of question we are looking at? We have feature X, and we have some sensitive attribute X. We have label. Okay, basically we have this triplet. We observe this triplet. Now, what kind of sensitive variable we may have? For example, we can have sex, race, age, disability, and so on, And we want to build a fair quantile prediction, under certain fairness. In this project, we adopt this DP fairness. This DP is not differential privacy, it's demographic parity, this DP fairness. Okay, that's our task. Now, what does that mean? What does it mean for this sort of demographic parity fairness? And here we have two groups. This dashed blue is one group. This long dashed blue is another group. And here are their distribution. Given Q alpha, and for this short dashed blue, the Q alpha quantile is here. For this other group, its quantile is here. However, we want to give a quantile estimate that is not sensitive to this. It's independent to the sensitive variable. That means it's independent of the group. Eventually, we want to get something here and something here. And it turned out this target one, this orange target one, is sort of eventually going to be a convex combination of these two convex combination. So our goal is to try to find this, Okay. So what did we do in this project? We basically bridged the gap on quantile demographic parity facts. Like I said, it's more important to examine the fairness at different quantile levels instead of just look at the mean, because this sort of fairness and disparity may be more serious and usually overlooked and be masked by sort of mean, right? And that's why we are trying to look at this quantile DP fairness. Okay, and we want to find this sort of DP fairness constraint quantile estimate. In instance, we use similar technique as previous. We want to find a distributional versus then to barrier center through this sort of optimal transport step. This is a key component of our technique. And on the behalf of that, we also incorporate sort of a kernel-based functional synchronization step. And in instance, when we estimate this quantile quantile function or distribution function, we actually using this sort of kernel smoothing technique. And this in particular is useful for if the group is small, the subgroup is small, the size of subgroup is small. And the approach we use is still this post-processing approach. Now here is the illustration of the pipeline for this DP fair quantile, And again, we have a sensitive variable S. We have two groups, and we look at this quantile regression. So like I said, during the training of quantile regression, and we don't do anything. You can use any method you like to train this sort of quantile regression. Now afterwards, we look at these two groups. We look at the distribution of these two groups. And when S equals 1, S equals 2, we estimate the cumulative distribution function and also the quantile function of this quantile estimate for each subgroup. Okay. For each subgroup. And then we use this distributional barrier center through this CDF and QF to find this fairness estimate. And here, a little bit different from previous is during the functional synchronization process, we actually using kernel smoothing to find a sort of smooth version of this empirical CDF and QF. Like I said, it's capable to deal with the small size of a subgroup. Now, through this process, can we, guarantee this sort of fairness? The answer is yes. We would have this fair optimal prediction. Okay, so we have, let's say, sensitive variable S, and we have a univariate measure that have a density function, and then this Q tau XS is a quantile estimate. Our goal is, this is after the training process. We are post-processing, right? Once we get this quantile estimate, we want to find this fair estimate, G tau xs. So we look at this expected mean square error to minimize this one. And to minimize this one, it turned out to be minimize this one. This S is for each sensitive group, And this one looks, this minimization of one looks sort of hard to optimize, but essentially it can be, we show that it can be written as this format. This fair estimate G tau xs essentially can be written as this sort of through this functional synchronization process. This Q tau xs is the estimate, quantile estimate we have, and then it get composite with this distribution function at S group, and then it composite with the quantile function for each all the other group, all the group in the for the sensitive variable. Then we take the combination of this, and this essentially the fair estimate, and yeah, as you can see, this fair estimate essentially is sort of weighted combination of this previous estimate of the previous estimate. Now, in order to, like I said, in order to build this cumulative distribution function and a quantile function estimate for each category, we can use the empirical distribution function, and here we use kernel smoothing to make our quantile estimate smoother, and so that we can deal with the small sample size situation. Now, the reason we want to have this smoothing step is I have two reasons. One is sometimes, the subgroup are small, and the subgroup is small. When we estimate mean, usually that's no problem. But quantile, it can be very, very different, especially when you look at when you want to estimate some quantile in the tail part, and you also have this small sample size, and then it can cause a lot of problems. The estimate can be very nauseous, and also this kernel smoothing can improve this sort of second order efficiency by elevating the relative deficiency, and it doesn't matter what kind of kernel smoothing you use, and although in our project we actually choose the Gaussian, but essentially it's not that critical what kind of kernel you choose. Okay, after we get this, the question would be whether indeed we would have this sort of demographic parity guarantee. The answer is yes. After we go through all this process, the estimate G alpha hat XS indeed satisfy this DP fairness requirement. So in a sense, we indeed have a situation, we have the estimate of the quantile, and then we can do the post-processing through our procedure, and then we can get a DP fair quantile estimate. The data set we look at is we have these 4 data set, and actually those data set are all sort of benchmark data set. We have this law school data set. This sensitive variable here is gender, and we look at the students' GPA, and based on their information and capacity. The second dataset is community and crime. The dataset contains social, economic, and crime data on the communities in the US with about 2,000 examples. The task here is we want to predict the number of violent crimes with race as a sensitive variable. The third dataset is sort of MEPS 2016. This dataset contains information on individuals and their utilization of medical service. The goal is to predict the healthcare system utilization score of each individual. And once again, race is the sensitive attributes here. They basically have two classes, white and non-white. The fourth dataset is government salary. The government salary dataset is collected from this 2018 American Community Survey by the US Census Bureau. The response is yearly salary. And the sensitive variable is employee rates. Employee rates. We have 7 categories here. This is the 4 benchmark dataset we are going to use. Here is the illustration of the method, and this triangle one is our method. Triangle one is our method. We also look at this square one is before we do post-processing. And this star and this diamond one is some other competing method. And how to read this this graph? This graph left is sort of measure whether it's fairness or not. And this side of measure is mean absolute error. As you can see, if you don't do the post-processing, apparently those methods are not fair, right? Because to the most left is most fair. And as we can see, our method is more fair than other methods. We also look at this computational time, and the reason we look at this computation time is during the review process, and this paper actually was just accepted by this NIPS of this year. And during the process, one reviewer questioned whether the smoothing process will add the more computational burden. And answer is yes, but it won't significantly add the computational burden. Like I said, this paper was accepted by NIPS, but it seems it's not that many. If we just we have this sort of a mean, right? Now we change it to this quantile, although it's quite appealing. Quantile is more reasonable, more appealing than mean, but maybe we also show all these necessary property, but maybe that's still not enough. Here is the other thing we did, which contributed to this literature significantly. Here is the thing is, we provide this fair estimate, and that's usually only first step. I'm a statistician. I also care about the uncertainty, uncertainty. So we are not only focusing on whether it's fair or not, we also want to look at to quantify the uncertainty of our fair estimate of our fair estimate. Therefore, we provide a way to provide to have this prediction interval, not just predict. Okay, predict. So the tool we are using is sort of this conformal fair prediction. Conformal fair prediction. Why we use conformal prediction? Because this method can measure this uncertainty without distribution assumption, especially for small samples. This sort of distribution assumption is very important because let's recall we are actually doing post-processing, okay, and we claim we don't have what kind of method used when you get the quantile predictor, right? In essence, we don't know what's going on over there. We only have this, quantile predictor, and not mention sort of distributional assumption and so on. So our method should be able to deal with this. And yes, indeed, this conformal prediction can deal with this. You just give me the estimate, and then I can deal with I don't need this distribution assumption. And also, not only that, our prediction interval indeed can guarantee for the error rate. And it can be used with any learning algorithm. And in particular for quantile, we use conformal prediction. We can provide this sort of robustness, and also for smaller prediction set size. This is also important. You are dealing with quantile as a tail part, even though the sample size may be reasonable, but as a tail part, less information available, and a lot of times the sample size can be an issue. Okay, now let's look at what's this sort of conformal quantile prediction. We have this IID data and XI, YI from distribution PXY. We don't know what kind of prediction. And we can take any arbitrary prediction model as input and calibrate it to produce a prediction set, C hat X, so that we can guarantee the marginal coverage. So, which means this property holds. Now, with the estimation of conformal quantile regression, essentially it's a variation of this conformal inference. So we need to predict an interval estimate in this format. As Q hat alpha low, this lower quantile, minus eta, this estimate of higher quantile plus eta. This Q hat alpha low and Q hat alpha high are the alpha lows, alpha highs conditional quantile. And this eta is this one. And this is essentially the calibration constant. This calibration constant can be used, is used to calibrate our prediction set so that it will have this sort of marginal convergence guarantee. Okay, so let's put it together. Our sort of conformal quantile regression works like this. We have sort of the data is get into three parts, and we have a training, we have a calibration. Okay, training, we get the model, and then we can get this prediction interval, and we get the corresponding conformal score. We get this quantile conformative score, and using calibration, and then together we can get the calibrated prediction interval. And then we can apply it to this test set. And in the test set, it will guarantee this coverage rate. So this is is sort of a split conformal fair quantile prediction, because for this conformal inference, we use the split word. We use a split word, and all the previous would be the same, and we can use any learning model to get a quantile estimate. And before that, of course, we split data into two parts. And one part we use it to do training. The other part we do calibration so that we can get this prediction interval. Okay. Now let's say, well, based on the training set I1, and we can train the model, and then we use the post-processing so that we can get the fair estimate. We can get the fair estimate, and then we use I2. Okay. As calibration set, we can get the conformity score. Then we can get this calibration constant. And then we put it in. Then we can get this conformal fair quantile prediction, because these are fair estimate, and also we get this calibration. Okay, like I said, this is we want to use this sort of conformal quantile prediction to quantify this uncertainty, and to quantify the uncertainty so that we would be able to, guarantee this sort of coverage rate. And indeed, we are able to guarantee this coverage rate. And for this conformal fair quantile prediction, this algorithm, we would have this for the n+1 observation, and we would have y n+1 in this interval, the probability greater than or equal to 1 minus alpha. Okay, alpha, and less than 1 minus alpha plus this part. As you can see the price we need to pay is this part, and this part is related to the size of the calibration set. So this calibration set is the larger the better, but of course the larger than the I1 will be small, then the training might be not that good. Okay, and here is the performance of conformal fair quantile prediction on these four dataset: this law dataset, crime dataset, MEPS, and government dataset. And as you can see, without this fairness, the coverage are close to this with this fairness. However, with fairness, the length of this prediction interval might be larger, because we need to put this fairness constraint there, and the price we need to pay is, as you can see here, the prediction interval might be larger. But on the other hand, the fairness measure of our fair quantile prediction is much smaller than the without this fairness adjustment. Okay, I think as a recap, so in this project we look at this demographic parity quantile fairness, and we provide a framework so that we can have this fair quantile prediction, and also we add this kernel smoothing to be able to deal with sort of smaller sample size situation. And not only that, we provide a novel conformalized fair quantile regression prediction. Right? Regression prediction. It can provide a way to quantify the uncertainty of this fair quantile prediction. And our method actually outperform some the state of the art fairness adjustment. Yeah. I think I will stop here.
Thank you very much. That was very interesting. Okay, if I can ask a question, I sort of think of the goals of fairness is to make appropriate decision, decide who should get a loan or who should be released from jail. If we use your approach versus just using the means, how will that change those decisions? Can you give me an example of where it gives a different decision and a better one? First,
well, in terms of fairness, yes, we would be able to get better decisions. Okay, because for example, let's put it in this way: whether you get along or not should not relate to your gender, right?
Yep, yep.
And in this way, we can guarantee the conclusion or the decision whether you get along or not is independent of your gender.
Right.
Yeah.
But isn't that true for fairness in general? That's the same goal as the more traditional fairness measures, I think. Or maybe I'm confused.
What would be my more traditional fairness?
Just looking at the mean values, for example. Maybe I should read your paper and look at it more carefully. I'm just trying to figure out where this would make a difference.
Oh, you mean quantile or mean?
For example, can you give an example where it's really obvious that if you just using the mean to make a decision which is wrong here, but the quantile approach, it's so obvious this will be the right decision to make, about the gender.
The mean, sometimes the mean just mask. For example, this okay, let's say the male and female, whether you get along or the income situation is maybe very different in the tail part. And the mean, well, if you look at the mean, and it may be fair. You don't want to say, okay, on average, it's fair. But you think about when we make policy, we would treat, low income, the low income situation, right? And in a sense, we actually look at those quantiles instead of, okay, when we make policy, we on average, we do certain things, right?
Okay, thank you.
Thank you, Raj.
So Professor, I have one small question. You talk about how to calculate the fairness in your approach, and did you try is the way you're calculating the fairness matters for the results? And have you?
Yeah, of course. That's why at the beginning, this also this is a very good question in a sense. Let's put it in this way. Even in sociologies, how to define the fairness is a sort of always ongoing debate. And so that's why at the beginning, as you can see, there are many ways to define those fairness. And of course, during the calculation, how how you define the fairness will, of course, affect the result. And if you can recall, like a couple of years ago, I say it's the trio on this Harvard admit Asian student or not, and these two economists, they have different way to to define whether it's fair or not, and they have different calculation. You may have different, a different result, and yeah.
Okay, thank you. Well, I think that's all for today's seminar, and thanks again for Professor Linglong's active talk. And okay, so I think yeah, thanks again for Professor, and yeah, so thanks everyone.
Yeah, thank you, and have a good holiday.
Yeah, you too. Yeah, bye.
Bye.